Okay, in today's video, what we're going to do is we're going to do a couple of examples to show you how Bernoulli's equation works. Okay, so the example that we're going to do, we take a look at this figure here up at the top of the slide. We'll see that we have a piping system. The piping system starts off with a 1/2 meter diameter pipe. Then it basically channels down to a quarter of a meter pipe. And then it drops 25 meters at that point. So we have a change in height and the diameter at 0.3 here. You can see I have 3 points labeled: 0.1, which is in the wider diameter, 0.2, which is in the smaller diameter, and 0.3, which is after the drop. Okay, we're going to say that the static pressure is the same throughout. We're going to say it's about 15 pascals, and we know the velocity at one point is 2 meters per second. What we want to do is we want to find out some information at points 1 and 3. We're going to look at 0.3 first. At 0.3, we want to learn what the velocity is. Okay. Now with Bernoulli's equation, what we can do is we can say the fluid relationship, or the energy at 0.2 is the same at 0.3. So we set up, since Bernoulli's equation is equal to a constant, the constant has to be the same. So we'll set up Bernoulli's terms on one side at 0.2. All these apply at 0.2. And then we'll set up the other side where all the same terms apply at 0.3. So I want you to take special notice, because this is the way you're going to set up all of your problems with Bernoulli's equation. Okay, you're going to set up Bernoulli's equation at one point on one side, and Bernoulli's equation at another point on the other side. So this is not the same P necessarily. These are the different values that apply at the different points. Okay, now since the P is constant, it can drop out. So you can see we've crossed out the P. Okay, and the height at 0.3 is going to be 0. The height here at 0.2 is 25, because we know it goes up 25 meters. Okay, so since this height here is 0, that crosses that term out. So this is going to help simplify the equation so we can solve it a little bit easier. Okay, we can look up the values from our reference chart, reference document, and fill in the values that we need. Okay, and when we do that, the 15 is there. We have this 2 filled in because that's given information. The density we looked up from the chart, and the specific gravity we looked up there as well. Okay, and we have the height, and we can see that these other terms cancel out. What we can do is simplify this out. I went ahead and wrote everything out that we can see that I've considered everything, and then I've simplified it here, and we can use algebra to find the value that we need. So I go ahead and simplify this term to 1998. I simplify this term to 245. And I'm simplifying this term to 499.5 V2 squared. Okay, and I go ahead and do some algebra, and I go through and I find out that my velocity at 0.2 is 2.12. Sorry, my velocity should be at 0.3. So we'll go ahead and correct that. That should be velocity at 0.3. And the same down here. I apologize about that. Net velocity is 2.12 meters per second. Okay, so that's it for that particular example. Now we're going to take the same problem and we're going to work our way backwards. We figured out the values at 0.2. We figured out the values at 0.3. Now we're going to figure out the values at 0.1. Okay, so we can say that the fluid relationship at 0.1 is the same as the fluid relationship at 0.2. So we've written out Bernoulli's equation, and we put our subscripts 1 and 2 here to apply to the two different sides. But since the P is constant, the heights are the same, those will also drop out, and the densities are the same, we can simplify the equation. We can use a simplified form for Bernoulli's equation, and that's going to be the flow rate equation. Okay, so the flow rate, the variable that we use for flow rate is Q. So Q1 equals Q2, and we expand it out. It's A1V1 equals A2V2. And I've gone ahead and calculated the areas for us. Okay, the 0.25 area is 0.1963, and the area for the quarter diameter is 0.0491. So we can see that this area applies here at 0.1 and this area applies here at 0.2. So we go ahead and fill these values in, and then we solve for V1 with some algebra, and we can see that we actually have a velocity of 0.5 meters per second. So you can see that it greatly increases from a half a meter per second to 2 meters per second. Okay? Now that concludes the examples for that. I do want to also talk about a vehicle example. In some cases, we're going to have to do a problem with a vehicle where we want to know what the pressure will be on the front of the vehicle when it's traveling. In order to solve these problems, we have to imagine that the vehicle is in an air tunnel, that it's stationary, and that the air is flowing around it at the same velocity the vehicle would be traveling. So we're pretending that this, because that's really the only way that we can set up this problem to solve for that pressure. So this vehicle, in this case, it's a plane. It could be a car. It could be a water tank. It could be a submarine. It could be a boat. It could be many different things. We're going to assume that the vehicle is stationary inside of an air tunnel, and the air is moving around it. Okay, so the air is moving before it touches the plane, and then this second point is going to be the instant the air touches the plane. Okay, so we're going to go ahead and set up Bernoulli's equation to do that. One side is the air in front of the vehicle, and the other side is the instant the air hits the front of the vehicle, so the instantaneous contact. We can simplify the equation with a couple things that we know. Now we're going to assume that the elevation is constant, so that means the hydrostatic term, this gamma H on both sides, is going to basically drop out, okay? And then we're going to also see that the instant that the air hits the very front of the vehicle, its velocity has to go to 0. You can actually test this. If you take a ball or you take something and let's say you throw it at the wall, the very second that it hits the wall, its velocity goes to 0. So that means that this dynamic pressure term is also going to cancel out when it contacts. So I'm going to have 3 terms that are going to cancel out. So I'll go to the next slide. There's my Bernoulli's equation, and I simplify it. You'll see that my hydrostatic terms drop out, and my dynamic term on the contact side also drops out. And it simplifies to this, okay? So the pressure when the air makes contact to the vehicle is going to be equal to these values here, okay? We can look up the values that we need for the problem. Really, we only need the density of air, okay? And this p-value should have been given to us in the problem to begin with, okay? This is going to allow us to determine if there's any issue with the static pressure that would crush the front of the vehicle. So again, when you get this simplified equation for any vehicle problem, this velocity is the velocity that the vehicle is traveling. The density you'll have to look up is the air or the water that's traveling around the vehicle. This P is the pressure of the air or the pressure of the fluid that's flowing around the vehicle. And this is going to be the contact pressure on the front. Okay? So you can very simply solve for that value.